A challenge into a duel, a wisdom duel. These are testing.
Welcome to Wisdom Jewels.
Okay, Tenzin, Rabga. So we'll be debating today about quantum physics. And within quantum physics, out of all the very many profound and sometimes difficult questions, we'll focus on sort of foundational questions. So looking at what is a wave function, probability function or wave function, and the wave-particle duality. What does that mean? And maybe just the nature of fundamental particles themselves. Of course, seeing what we have time for, but within that general area. Okay, so I'm gonna start. So we start with the digital chechen, and so let me just start by saying it follows that if something is an object, it necessarily has an associated wave function.
I accept.
Okay, so it follows if something exists, it necessarily has an associated wave function.
I accept.
Okay, and so take the subject, a cat, it follows they have an associated wave function.
I accept.
Okay, so there's one for macroscopic objects, and then like for instance, an electron, take an electron, it follows that it also has a wave function.
I accept.
Okay, so it's whatever size object, no difference, anything that exists. Okay, good. Now, so if we establish that objects have wave functions, then maybe we can ask, so what is a wave function? So can you posit the definition of a wave function?
The wave function is, okay, how do I define a wave function? The wave function is, in the most strict sense, is the solution to what we would call, is the Schrodinger equation, which essentially describes the dynamic of the object or the particle.
Take the subject, the solution of the Schrodinger equation, which describes the dynamics of the object, it follows that as the definition of a wave function.
Yes.
Okay, so the solution of the Schrodinger equation, and the Schrodinger equation is the one where it's can you state the Schrodinger equation?
Okay, so the Schrodinger equation is essentially the content of okay, let me find a good way to describe the Schrodinger equation, because so far I've always done it mathematically. I've never thought of it in terms of words. Essentially what it does is it's an equation, and it essentially contains you could say the energy content of the system. But I use that word energy in a very loose sense. The technical word is Hamiltonian, which is more often than not similar to energy. And that defines the state of the system. And that state of the system is the solution of that equation, which is the wave function.
So then take the subject, the Hamiltonian, which describes a system, it follows that is the Schrodinger equation's definition.
The Hamiltonian, which describes the dynamic time evolution of the system. That time evolution is encapsulated in the Schrodinger's equation. Yes.
So it's about the time evolution of the Hamiltonian, yes, which is like an energy.
Time evolution of the
system, of the state of the system.
Of the system. Yep.
And the Hamiltonian is related to the time evolution by being a description of it, or it is it? The Hamiltonian is the time evolution of the system?
The Hamiltonian drives the time evolution. In other words, the time evolution is driven by the Hamiltonian.
It's dependent on the Hamiltonian. So the Hamiltonian is, so let me take the subject of the Hamiltonian. It follows that it is a mathematical object or a physical object?
Only if I knew the difference between the two.
Oh, okay. Well, yes,
I would say it's the mathematical representation of a physical phenomena.
It's the mathematical representation. So the Hamiltonian, let's take the subject, the Hamiltonian, it follows that it doesn't actually have a physical presence in the material world.
I would say it does.
Okay.
I would say it does. Yes.
So take the subject, a Hamiltonian of a cat. It follows that it is a physical property of the cat.
Not it's a physical property of the cat. Why?
Because it is a property of the cat, and B, it is a physical object that exists in the material world.
The reason A is not true.
Take the subject, the Hamiltonian of the cat. It follows it is not a property of the cat.
I accept.
It's not
entirely the property of the cat. It involves terms that are interactions between the cat and the environment.
I see. So take the subject, the Hamiltonian. Let me ask a pervasion statement, pervasion question. It follows that if something is a Hamiltonian, then it is necessarily, I guess I could say, a composite of multiple systems.
Yes, I accept.
I see. Okay. So take this subject. So we're kind of laying out the Schrodinger's equation when we have this idea of a Hamiltonian. The solution to the Schrodinger's equation is the wave function. Hamiltonian is what drives the time, what was the word used? The evolution. Time evolution. And the Hamiltonian is sort of the heart of the Schrodinger equation. And now the Schrodinger equation, doesn't that also contain the h bar, the Planck's constant?
Oh yeah, it does.
So how is that? Can you say how that's related to the Hamiltonian?
Oh yeah. So so the dependence between the time, so what we would in mathematical terms we call the time derivative of the state vector, which is not the vector. Let's not get to the vector. State function, which is the wave function. The constant of proportionality between the two it depends on the h bar, or the h, or the Planck's constant. So it kind of sets the scale of the effect, of quantum effect, and this is a very small number. Yeah, so it's
like a scaling. It's something that's used to scale when you have a Hamiltonian on one side of the equation, you have a wave function on the other side of the equation, and the Planck's constant sets sort of it tempers the result of the equation.
It sets the scale at which the Hamiltonian affects the time evolution of the state.
Take the subject, the Hamiltonian of a cat. It follows that it either does or does not affect the evolution of the cat, the state of the cat.
I accept. Yeah.
Which one?
It does.
It does. So then even so, if something is if something is an object which you're describing or analyzing using Schrodinger's equation, it follows that the presence of the Planck constant there is necessarily not going to eliminate any effect of the Hamiltonian.
I accept.
So there's always some. So
yeah.
So you say. So I'm just trying to get it clear about what scaling means, because if it's no matter what size of object.
I mean the magnitude of the effect, like how big
the
of
magnitude of the effect. Yeah. Okay, cool. So this is getting some of the kind of foundational features of this kind of heart equation in quantum mechanics, the Schrodinger equation. So, but to be quite honest, I'm not conversant enough in the equation and the mathematics of it to really use that as a good jumping off point to get into some kind of nitty-gritty philosophy question. So I'll just kind of leave that and then go into just the nature of this wave function, because although I'm hearing what you're saying, I still don't quite clearly comprehend exactly what's going on to get from Schrodinger's equation with the Hamiltonian and Planck's constant to the wave function. But but just to sort of look at what that is. Anyway, so I'll take the subject, the wave function of a cat. So first of all, let me just say, so a wave function and probability function, take the subject, the wave function and the probability function follows that they are equivalent.
That they're equivalent.
Equivalent dunji.
Teacher.
Okay, so it follows that.
Why? Yeah, why?
It follows they're not equivalent.
I accept.
So it follows if something is a wave function, it is not necessarily a probability function.
Oh yeah, I accept. Yeah.
Okay, can you posit an example of that?
Oh, these two are gewa.
Well, so posit something which is a wave function, but not a probability function.
A wave function.
Oh, that's just a wave function. Take this subject, a wave function. It follows it's not a probability function.
Yes, I accept.
Because? It's not because?
Because it does not describe the probability of an event.
Oh, yes, I see. Take the subject. Okay, so okay, so take the subject, the wave function of an electron in that's being examined via the two-slit experiment, right? Double slit experiment.
Okay.
Okay, so it follows that it has a wave function.
I accept.
And it follows that if I make the statement, right? Take the statement. You say, let's take that as a subject. Take the statement that the wave function of the electron being examined via the double slit experiment is a probability. It describes the probability of finding the electron upon detection within a given space. That statement, it follows that that is not a correct statement, not a true statement.
I accept.
Okay, so take the subject, the wave function of the electron in said experiment follows that it is not a description of the likelihood or probability of finding the electron in a particular region because
it's not the electron's probability function.
I see. So take the subject, the electron's probability function, it follows that, so let me ask this. So take the subject, the wave nature, right? Take the subject of an electron. It follows it has both a wave-like nature and a particle-like nature.
Nature. Does it have a nature that's wave-like or particle? Oh, okay. I'll have to think about that. Okay, I accept.
Okay. I mean, that's a commonly said statement, but of course you don't have to accept it. So, okay. So if it has a wave-like nature and a particle-like nature, and so let me just say, so the explanation.
Okay. I'd like to go back. Take that back. I'll ask you why.
Why? Okay, take the subject, an electron follows it does not have both a wave-like nature and a particle-like nature.
I accept.
It follows it has both a wave-like nature and a particle-like nature because through the observations of the double slit experiment, when there is a detector placed on one of the slits, it exhibits a particle behavior, and when there's no detector on one of the slits, it exhibits a wave-like behavior. That's the reason.
No pervasion.
No pervasion. Okay, so it follows that simply because of simply because of having difference in detection in your experimental design, resulting in the observation of particle versus wave behaviors, does not necessarily mean that that object being analyzed has both particle and wave natures.
I accept.
Okay, so take the subject an electron, it follows that it has neither a particle nature nor a wave nature.
I accept.
I see. Interesting. All right, where to go now? Take the subject an electron, it follows it is not a particle.
Not a particle. Well, you haven't defined a particle yet, so.
Well, that's very great. We have a chance to do it.
All right. You said take an electron. It's not a particle. I accept.
It's not a particle. Okay. So take the subject, the standard model of particle physics, with the bosons and fermions and so forth. It follows that it does not contain any particles.
It does not contain any particles.
Well, it does not describe, particles are not part of the model.
I accept.
Okay, take the subject of particle, it follows it just doesn't exist.
Particle doesn't exist. Okay, I accept. Yeah.
Take the subject. Take the subject, an electron. It follows it is not a quantum object.
Why?
Because it's not quantized.
Not a quantum object because it's not quantized. Reason's not true.
Follows it is quantized.
I accept.
Follows it is not quantized because it is not localized within a region of space.
No pervasion.
Follows that if something is not localized within a region of space, it is not necessarily not quantized.
I accept.
Take the subject, an electron. It follows that it is not localized within a region of space.
Within a region of space. I accept. Okay.
Yeah, that by saying no pervasion, you basically accepted that, right? You could always change it. So if it is not localized in a region of space, take the subject. Let me put it this way.
Wait.
If something
take
is
an electron. Okay, yeah, no, that's fine. Yeah.
All right. Take the subject, an electron in the two-slit experiment at, MIT, whatever, in a lab at MIT. It follows that it is not localized in space.
Yeah, I accept.
It follows it is localized in space because it is localized in Massachusetts, United States.
It's localized in space because it's localized in Massachusetts. Okay, I guess. Yeah, okay, I accept.
Okay, so now we give a strike. So you've gone back on. So it follows it is localized in space.
I guess my trouble with that statement is, and there's no way to bring it out in this debate, is you said an electron is localized in space, but each electron is different.
Well, so now now the subject is the electron in the two-slit experiment in a lab at MIT. Right.
Yeah, that is localized in space. Yes.
Oh, okay. So that's localized in space. So you said electron, the subject electron is not localized in space. So now the statement of pervasion, though, if something is an electron, it follows it is not necessarily not localized in space.
Okay, you know what? Okay, I'll go back all together and say, okay, if it is an electron, then it is localized in space, in the sense that, because, okay, by localized, I guess we haven't fully described what localized means.
Okay.
Okay.
So let me ask you, take the subject.
All right, it is localized in space. Yeah, okay.
Okay, strike. Okay, so take the subject, the electron at the lab at MIT, in the two-slit experiment. It follows that there is a probability of locating it. That's the question. There's a probability of locating it.
Yeah. Yes, I accept.
It follows that there's a probability of locating it in Cambridge, Mass.
Yes.
Okay, can you state what the probability is?
What can I state? It's rather high. I can't state quantitative probability.
Okay. Take the subject. The probability of finding the electron which is in the lab at MIT, in in Massachusetts, it follows that it is not 100%.
It's not 100%. Yeah. Yes. I accept
it is 100% because it is located because it is known to be located in Massachusetts.
The reason's not true.
It follows it is known to be located in Massachusetts because it is known to be located at MIT.
The reason's not true.
It follows it is known to be located at MIT because it is located at MIT.
The reason's not true.
It follows it is located at MIT because it is an electron which is located at MIT.
The reason's not true.
Take the subject, an electron located in the lab at MIT, follows it is not located, an electron located in a lab at MIT.
The very description, take the subject, electron located at MIT is not correct. So
Take the subject, an electron located at a lab at MIT, it follows it doesn't exist.
yeah.
So take the subject, if something is an electron,
yeah.
it necessarily is not located at MIT.
Yeah. All right, I'll probably have to take a step back because, all right, so because we haven't quite gotten to the question of measurement yet.
Okay, so let's take a step back and maybe shift gears to the question of measurement before we locate something. Now, let me just clarify, just the, so the confusion or the tricky question here is, does it have to do with the fact that there's a certain probability associated with locating the electron, which is not 100%?
At the other end of the universe, yeah.
Right.
There's
so
a non-zero probability.
Well, okay, so then let me just say though, so then the subject, the electron at MIT, if we really, let me say it this way, if something is an electron, it follows that there does not exist a human being who is certain of its location at MIT.
Okay, with a bit of a hindsight, I will say I'll ask you why.
Okay, so it follows there does exist a human being who has 100% certainty, I should say, factually concordant certainty that the electron is located at MIT. And
I accept.
And take the subject, a human who just conducted a two-slit experiment at a lab at MIT, and follows they are such a human.
Yes.
Okay, so you can come up with a condition in which there is 100% certainty of the location of an electron.
Mm-hmm.
Oh, okay. So take the subject. So if something is an electron, it follows it is not necessarily. So let's put it this way. So take the subject, the electron, which is known with factual certainty by an experimenter to be at MIT, it follows that its probability function, its probability of being located at MIT is 100%.
I accept, yes.
Take the subject, an electron at a lab at MIT, it follows that its probability of being in MIT is 100%.
Yeah, I accept.
Okay, so it follows that there is not a non-zero probability of it being at the other end of the universe.
I accept.
Oh, strike. So take this. So if something is an electron, it necessarily has no. If something is an electron which is not at the other end of the universe, it follows it is necessarily has a zero probability of being at the other end of the universe.
If it's not at the other end of the universe, then there's a zero probability. Why?
Okay, if something is an electron which is not at the other end of the universe, it does not have a zero probability of being at the other end of the universe.
Which is not. I guess, are you then implying that it is somewhere?
That seems to be what I'm talking about. If it's not at the other end of the universe, then it's somewhere else other than the other end of the universe.
Okay, so here's the trouble because.
Okay, why don't you draw up the trouble?
Of course, I guess we'll step out of the debate mode a little bit, and I'll just explain to you what the trouble is.
Okay.
The trouble isn't thinking, because when you make these statements, I'm trying to think of in terms of whether it is pre or post measurement.
Right.
Pre-measurement to say that electron is somewhere is quite nonsensical, because it could be, anywhere with a non-zero probability. But again, I mean, not necessarily. But it depends again on that Hamiltonian. It depends on how it's quantized and wave function and all that.
Okay.
But post measurement, then you have absolute certainty where it is.
Okay. So take the subject an electron. Good. So it follows that pre-measurement there's no certainty as to its location, but post measurement there is certainty as to its location.
Okay. Pre-measurement, there's no certainty as to its location, but post-measurement, yeah. Is that true most of the times? Okay, I accept. Yeah, okay, let's go.
Okay. So take the subject an electron. So there's a lot of questions that can come from this, but so let's go back again though to an earlier thing that came up was, so take the subject an electron, right? So you already accepted it has no particle nature, right? If that's not a particle. Okay, so if something is an electron, it follows it is necessarily not a particle.
Necessarily not a particle. Yeah, okay, I accept.
And it's necessarily not localized in space, right?
Yeah.
Okay, take the subject of the electron
post measurement. It's necessarily not localized in space. Why?
Okay, so it's not necessarily not localized in space. Okay, so
yes, I accept.
So before we were saying I said it wasn't quantized because it wasn't localized in space, and you said no pervasion. So, but you're saying now it could be localized in space.
Yeah. Yes.
Okay. So take the subject an electron post measurement. It follows that it is localized in space.
I agree. I accept.
It follows that it is a particle.
Follows that it is a particle. Why?
Because it is an object with a quantifiable amount of energy that is localized in space.
No pervasion.
Okay, so if something is something is an object with a quantifiable amount of energy that is localized in space, it isn't necessarily a particle.
Yeah, I accept.
So.
Okay, yeah, I know where this is gonna go, but yes.
Well, so I mean, you already accepted that particles don't exist, basically, right? I mean, we didn't hammer into that question, but
right.
So let me just ask take the subject particle. It follows it doesn't exist because, and you can give your reason.
Particle doesn't exist because there's no instance of a particle. It's an ideal concept.
So it follows that there's no instance of a quantized object.
Why?
Because because it is an idealized object.
That's not true. The reason's not true.
Okay, so it follows if something exists, it is not necessarily not a quantized object.
Something exists and it's not necessarily not a quantized object. Two negations.
That's just a backwards way of asking you to give an example. So I'm just, I mean, it's the backdoor way of just saying, what's an example of a quantized object?
Okay. Yeah, I accept. Yeah.
Yeah. So can you posit a quantized object?
An electron in an atom.
Take the subject, an electron in an atom. It follows it is quantized.
I accept.
It follows that it is particleized.
Why?
Because it is quantized and there's no other property that needs to have in order to be particleized.
No pervasion.
But you're accepting that it doesn't have to have any other. My point is asking what quality other than being quantized would need to have to be particle.
Okay.
Yeah.
what other property would it have to be? So I guess here, quantized. I'm probably using quantized in a very different way. So we could probably try and define quantized.
Take the subject, the electron in an atom. It follows that it is not a particle, right? It follows that. So if something, I can't say if something is a particle, if nothing is a particle, but let me just say, in the idealized imagination of a particle, then if something is a particle, it necessarily has a completely well-defined boundary.
Completely, it must necessarily have a complete, yeah, except.
And so then if something is an existent object, it necessarily does not have a completely well-defined boundary. Moving to reality.
You say that again? No.
Right, so if the idealized particle has a well-defined boundary, and you're not accepting that exists, so then so let me just ask, so take the subject, an object with a well-defined boundary. Leave the word particle out. It follows that either exists or does not exist.
Does not exist.
It does not exist, okay. And that is the reason for why you don't accept particles to exist.
Yes.
Okay, take this subject. Okay, cool. So, take the subject, a pebble. It follows it is not a particle.
Subject, a pebble, it's not a particle. Yeah, I accept.
Follows it is a particle because it's an object with a well-defined boundary.
The reason's not true.
It follows it's an object with a well-defined boundary because it is defined by, it is defined in human perception.
No provision.
So if something is defined in human perception, so that's how I said it. So if something is defined in human perception, it is. So it has because it is defined. I guess what I meant to say is the boundary is defined in human perception, right? And you would still say no privation.
Yeah.
Okay, so if an object's boundary is well defined in human perception, it is not necessarily well defined. The boundary is not necessarily well defined. Okay.
Yes, I accept.
Okay. Why? Or take the subject of route.
Yeah, okay.
Why is its boundary not well defined? Yeah.
It's made up of atoms that it has atoms on its edges with electrons that are not, well bounded, don't have a well defined boundary.
Okay, take the subject, an electron. It follows that it has, other pieces of it which are on its boundary that are not well defined. Say the electron in the lab at MIT. We'll go back to that electron. It follows that it has pieces which are on its boundary that are not well defined because it is an object which is A, defined in human perception. Its boundaries are well defined in human perception, but B, in reality, its boundaries are not well defined. Like the pebble.
Okay, so do I say the reason's not true, or I feel like both could apply, but I'm trying to find the correct one.
Well, normally, if you think the reason's not true, you would go with that one, right? If both apply, you would go with the reason's not true because that's sort of the more.
Yeah, okay, the reason's not true. Yeah.
Reason A or B? The reason A again was.
Yeah, could you repeat that again? Yeah.
Reason A again is that its boundaries are well defined in human perception, but its boundaries in reality are not well defined, or just are not well defined. So you would accept B. You would accept B probably.
And the B is accepted. The A is questionable since I don't know if he observes the electron.
So take the subject, the electron at the lab at MIT, and I'll say actually the electron at the lab at MIT post measurement. Okay, just to make it very precise. Does that change the whole thing? So
yeah, that changes a little bit. Yeah.
Okay, well, let's stick with that one though. So that object, it follows that its boundaries are also not well defined, right? because it's not a
Boundaries
particle.
are not well defined. That is post measurement.
Mm.
So you're talking about the post measurement. Its boundaries are not well defined. Why?
Ooh, follows its boundaries are
Okay,
not well
so
defined because it's not a particle.
no. I was still under the assumption we're talking about the pebble.
Oh, okay, right. So now going to the electron at the lab at MIT post measurement.
That has a well-defined boundary.
It follows it does not have a well-defined boundary because it is not a particle.
No privation.
Okay, so it follows that not having a well-defined boundary. Well, I know the style is just to repeat the thing for clarity. So, but you said no pervasion, I'll just say it again. So it follows that if something is not a particle, it isn't the case that it necessarily does not have a well-defined boundary.
Yeah, I accept.
Okay, so take that subject not having a well-defined boundary. It follows that is not your reason for not accepting the existence of particles.
Yeah, I accept.
Okay, so what was the reason for? So take the subject that electron post measurement, the lab at MIT. It follows it is not a particle because
it's not.
You said it's an idealized object at first, so you could still say that, but what I'm trying to get at is
it's
what
not
about
a particle
it?
Because because it doesn't satisfy the criteria for being a particle.
It follows it satisfies the criteria for being a particle because it satisfies the criteria of being a matter, being B, localized in space, and being C, clearly defined in both human perception and in reality, having boundaries which are both clearly defined in perception and in reality.
No privation.
Okay, so that was my question though. So what would be the quality of a particle?
It's missing one criterion.
Okay, what's that?
That is, it has a well-defined, it's localized in space, it's a matter and all those properties all throughout time.
So something were, so this is again going into the idealized version of particle, something were to be a particle, it would necessarily be unchanging all throughout time.
Yes.
So that's what a particle has to have. So then take the subject, the universe. It follows that it is not, take the subject, the universe. It follows that it is not localized in space, does not have a clearly defined boundary, and is not defined all throughout time.
Not defined all throughout time.
Throughout all time is not.
Well,
it's not. It doesn't have those. It does not have its properties throughout all time.
The reason is not true. The last one. It has properties all throughout time.
Right. So take the subject of the universe. It follows that it does not satisfy those criteria because it is not a particle.
Okay. Doesn't satisfy all those properties, all those criteria. It's because it's not a particle. No privation.
So something is not a particle. So, well, let me reverse it. Take the subject, the universe. It follows that it is a particle.
Why?
It follows it's a particle because it satisfies all the criteria of something, if something were to be a particle, it satisfies all the criteria necessary.
All the criteria of being a particle.
Mm-hmm.
Yeah, I accept. If something is a particle, then it's
no. I'm saying the universe. The universe is the subject. It follows it is a particle because it satisfies the criteria. Particle would need to satisfy it if they existed.
The reason is not true.
It follows it satisfies them because it satisfies the criteria of having properties which remain throughout time. It has a defined boundary and it has.
The reason is not true. The second one does not have a well-defined boundary.
Take the subject of the universe. It follows it does not have a well-defined boundary. it follows it has a well-defined boundary because that boundary is the extent of the universe.
Extent of the universe. The reason is not true.
Take the subject, the extent of the universe. It follows there's
I
not
mean,
the
the extent of
boundary
the,
of the universe.
well, okay, no privation. Okay, let's say no privation.
Okay, it doesn't have, so take the subject, the extent of the universe. It follows that is not a well-defined boundary.
Yes, I accept.
It's not well-defined because
it's made up of elementary particles whose probability waves stretch out into infinity.
So take the subject, the boundary of the universe. It follows it is infinite.
Yeah, I accept.
So take the subject infinity. It follows that is not clear. Say this way. Take the subject something with an infinite. As you can say, bounds that are infinite. Take something that is boundless. It follows that I'll say the word infinite because that's part of, okay. Take the subject something with infinite bounds. It follows that is not well defined. And take the subject infinity. It follows that is not a defining property.
In terms of localization, yeah, I accept. It could have other well-defined properties, but in terms of spatial localization, yeah, it does not.
Okay, so let's see if we can go back to that. So we had the electron, you're saying not remaining, the electron at the lab at MIT post-measurement does not remain that way throughout time. Does not keep its properties throughout time. So now this is just, without the actual quote, I'm not gonna, use it as debate fodder, but just I had heard from one physicist talking that the properties internally electrons are unchanged. They are unchanging. Is that not your perspective?
No, I guess you could posit internal properties, but position would not be one of them. Or
right.
Spatial
okay,
localization would not be one of them.
Mm-hmm.
Like the mass of the electron, that might be inherent. And
yeah, but
maybe
we're talking about the properties that enable that are its boundaries, right? Not its spatial location.
Yeah, but boundary has to do with spatial location.
So let's get. I mean, we're coming up on time, but let's see if you have a couple more minutes. We'll go to the question of measurement now because I think that's actually related to what's coming up now. Because it is pretty directly related, right? What are we even saying about the electron being bound or clearly defined? The bound with clear definition, or
that's where
having
all
a
the
spatial
confusion
location
comes in from. Yeah.
So now we have to move into measurement. Okay, going back to the very beginning with the Schrodinger equation wave function, because we didn't really go into the wave function yet. Now the wave function is also related to how something is measured, correct?
Related to how to. Okay, sure. Yes, it is. I accept.
Okay, so just to put it so take the subject. Well, let me put it this way. So actually, I'll ask you because we discussed it before, but haven't yet here. So take the subject. If something exists, it is necessarily an emergent phenomenon.
Why?
If something exists, it is not necessarily an emergent phenomenon.
I accept.
Okay, posit an example.
The electron.
The electron, okay. I thought you. So take the subject an electron. It follows it is not emergent.
Yeah.
It follows it is fundamental.
Okay. Yes, I accept.
It is okay. Okay, never mind. So if the electron is fundamental, no problem. So it follows that it is it exists fundamentally. So therefore, if I take the subject the electron, it follows that it exists independent of other factors. Is an independent entity.
I accept.
So it follows that it exists independent of measurement.
Yeah, I accept.
So it follows, take the subject, the electron, it follows that it take the subject, an electron independent of measurement. It follows that it is contradictory with an electron that has been measured.
Contradictory. That's okay.
Well, let me ask it this way. If something's an electron, is it necessarily independent of measurement?
Is it independent of measurement? Necessarily, no.
Okay, so what's an example of an electron which is dependent on measurement?
An electron that has been measured.
Okay, take the subject, an electron that has been measured. Right. It follows that it is at once an electron and also something which is dependent on measurement.
I accept.
It follows that it is not an electron.
Follows that it's not an electron. Why?
Because it is not fundamental.
The reason it's not true.
It follows that it is not fundamental because it is not independent. I should say because it is emergent.
Emergent. The reason it's not true.
It follows it is emergent because it is not independent.
No privation.
Okay, something is not independent. It is not necessarily emergent. So if something is dependent on other factors, it is not necessarily emergent.
Okay, I accept.
Okay, I don't know if emergence is the main thing I want to go into here, but but that was interesting to find out. Then the real question here we want to get to is measurement, though, right? So I'm just kind of trying to figure out the best way to get into the question of measurement, and I wonder if maybe we could just set up the double slit experiment. Don't have to kind of explain the whole thing, but just kind of you have the idea of it. So then a double slit experiment, it follows that there is something like an electron or photon which is measured, right?
Yeah, I accept.
And so it follows that the measurement is observer dependent or not observer dependent.
Observer dependent.
It is observer dependent. Okay. Take a subject, an electron in double slit experiment at the lab at MIT. It follows that the measurement of it is dependent on the observer conducting the experiment.
Why?
Because it is observer dependent.
Okay. Yeah, I guess we should have decided what observer means.
Right. Okay. There we go. So you could say, why, and then.
Yeah. Okay. Why?
So because it is A, observer dependent, and B, there's no other observer besides the experimenter.
Oh, the reason is not true.
Okay. So if there is another observer besides the experimenter.
The measuring apparatus.
The measuring apparatus. Okay. Take a subject, the measuring apparatus in the two-slit experiment. We'll just say two-slit experiment to condense the subject, but still, it's there over in MIT. So take the subject, the measuring apparatus in the two-slit experiment. It follows it is an observer.
I accept.
And it follows that if something is a physical object, it is necessarily an observer.
Something is a physical object and it's necessarily an observer. Yeah, I accept.
So take the subject, so I'll just back out a little bit and then take the subject, the electron that is not dependent on measurement. It follows that it is not in a physical system.
Yeah, I accept.
It follows it is in a physical system because it is in the system of the universe.
Okay. It's in the physical system. Okay. Yeah, I see what you mean. Yeah, yes. I'll go back and I'll say it is in a physical system. Yes.
Okay, straight. So it follows that it is not in a physical system because it is not interacting with other objects in the system.
The reason is not true.
Follows it is not interacting with other objects in the system because it is not being
Oh,
measured.
Sorry. Not reason's not true. No privation. That's what I meant.
Okay, so it follows that something is not
Yeah.
interaction with objects in the system. It isn't the case that it's necessarily not in the system.
Yes.
So it follows that it being in the system. Can you explain what it means to be in the system then?
To just be in the presence of other other objects, other physical
Well, it's
objects.
in the presence of them, but it has. So take the subject, an electron that's in a system but not interacting with the system. It follows that it also has a probability function.
Yeah, I accept.
And it follows that it has a superposition.
It has superposition.
What let me say it follows that
It's the reason is not true. It's not necessarily in a superposition.
so does it have it follows that it is entangled with other particles.
Is it entangled with other particles? No.
No, it's
Not necessarily.
Okay. Follows that. Okay, well, and it doesn't necessarily have a superposition. So it's.
So okay.
Yeah.
Here's the problem again. Whether or not an electron has a superposition depends on what's the right English word? Depends on your point of view. Let's put it that way.
Well, so
you could generally express it in a superposition, but you need not do so.
You could express it in a superposition, but you need not do so. So then if something doesn't have a superposition, right? If something is an object without a superposition, it follows that its position then is well defined with 100% probability.
Why?
Because there's no probability of it being in more than one location. There's no probability of it being at point A and point B.
All right, so I guess the reason's not true.
Follows there is no probability of it being at point A and point B because it doesn't have a superposition of point A and point B.
Oh, okay. That's not true. Okay.
It follows it
Why?
does have a superposition.
It does have a superposition. Okay. No, that's not true.
It doesn't have a superposition.
Well, okay. So here, that's okay. Yeah. Okay.
Is the probability? Yeah. What are you thinking? Go ahead.
Okay. So here the difficulty is because when we say superposition, what we mean by that in I guess quantum mechanical terms is that it can be expressed as a superposition of two states, two separate states. And an electron that is not localized need not be in two separate states. That's just one physical state that it's in. If that makes sense.
But isn't the property of non-localization simply a feature of it having a probability of being in various multiple locations? Yeah,
so that is what I meant by your perspective, because I can describe the situation in terms of, momentum states. I could describe the system in terms of position states. In terms of position states, it might be in a superposition, but in terms of momentum state, it might be in one momentum state. It's not in a superposition of momentum states.
Right. It could.
Yeah.
If it has a superposition of location states, is it necessarily not have a superposition of momentum states?
Yeah, that is.
And vice versa.
Yeah, and vice versa. Yeah.
So let's just look at location then. So let's take the subject an electron which is in a system, but not kind of setting up the properties, right? It's
Okay.
in a system, not interacting with any other objects in the system, and has and does not have a superposition of momentum states, right? It follows that electron has a superposition of position states.
Yes, I accept.
And so the superposition of position states, then, I mean, this is difficult for me to figure out how to ask it.
Yeah.
But I'm trying to just say, then doesn't that necessarily imply that, I mean, this is like my very unnuanced way of trying to phrase it, that it's sort of, moving into other objects, and so like it's not maintaining its boundaries, so therefore it's somehow interacting with other objects.
No, not necessarily. Technically, it's not interacting. Yeah.
Okay.
Because to have an interaction, you would need an interaction component in the Hamiltonian, which
So take the subject, that electron, though. It follows that there is knowledge of its state.
Sure. Yeah, I accept.
So this is an electron which is not interacting with any other physical objects, right? It follows there is knowledge of its state. So it follows that it is known by an observer.
Known by an observer. Why?
Because A, its properties are known, and B, the knower of those properties is an observer.
Without doing any measurements. Yeah, I guess you could have a knower. Yeah, okay. So in this case would be, I guess I would take a strike again. Yeah.
What
You could have no that there's no knowledge of its state.
But you said there
observer.
was knowledge of it, but there's an observer. Okay, so you're accepting there is an observer.
Does it have to be observed though?
Observed.
Yeah, this is tricky for me to fully unravel.
Sure.
Because here's the problem, because you're absolutely not doing any measurement here. But I know that the electron is not interacting with anything. And by the virtue of non-interaction, I can fully define its state mathematically. It's in what's called a stationary state. Like it's in a fixed energy state. Its energy is not going to change. So that much knowledge I have. But again, the knowledge of the state is different from the knowledge of its position, is what I would say.
Sure, but okay, but so we're just talking about, in general, having, right, being known or observed. So it follows that its state is observed.
Its state is observed. Its state is observed. Why?
Because it's known by an
It's
observer.
Yeah, I suppose so, without measurement. Yeah.
So it follows that it is being measured.
Why?
Because it is being observed by an observer.
No provision.
No provision. If something is observed by an observer, it is not necessarily measured.
It's observed by an observer. If it's being observed by an observer, then it's not being measured. I'll probably have to take back that it's being observed in the first place. Because that's so heavily tied to measurement in my head.
Oh, strike. So it follows it is not being observed.
Yeah, I accept.
It follows it is not being known.
Why?
It is not being known because it is not being known by an observer, and there's no other, because A, it's not being known by an observer, and B, it's not being known by a non-observer.
No privation.
So it follows if something is known, it's not necessarily known by either an observer or a non-observer? Is there a third
No,
party
if
by which it's being?
I meant to say that
Oh.
if it's known by an observer,
Hmm.
it's not necessarily the case that it's being observed.
Okay, so it's right. So it's known by an observer. It's not necessarily being observed. So that's why I said it's So then I said it's not being known. Well, that's just the same question. So you're just saying there's a difference between knowing and observing. Okay. So what I said, because it's known by an observer, but it's not observed. Okay, I see what you're saying. You're just limiting being the observation to something else. So take the subject right.
It's like knowing 2 squared is 4, but we don't measure or observe it.
So okay, right. So take the subject, observation. Yeah, I think I basically know what you're saying, but you're defining observation. So take the subject and observation. It follows it is necessarily, it follows it is. I'll just ask you to define. Can you define an observation? Maybe that's easy.
Measurement.
A measurement. Oh, good. Can you define now? Posit the definition of measurement.
The measurement is the measurement is the act of interaction between the object of measurement or the object of observation and some external physical object.
Right. So take the subject, the act of the interaction between the object being observed or measured and some other external physical object. It follows that is the meaning of a measurement.
I accept.
So take the subject, the electron that's not being measured. It follows that it is being. So let me say. So take the subject, the person who knows the state of the electron which isn't being measured. It follows they are not interacting with the electron.
I accept.
It follows that they're not interacting with it because?
They're not interacting with it because there's no interaction between the two.
Because there's an interaction between the two because there is the object appearing in the mind of the knower. The electron's properties are being known and entering into the conscious awareness of the knower.
No privation.
So it follows that entering into the an object entering into the conscious awareness of a knower is not a case of interaction with the knower. It's not because?
It's not because it's not affecting the electron in any way whatsoever.
So it follows that, all right. Well, we're getting pretty long, and this is a kind of a cool place to maybe leave it. But it's
probably
maybe
I feel kind of I'm ending on a better note after all the strikes.
Yes. You have a good position, but it's also another cool place that might be a good place to just, if we have a chance to go at it again, just to start off with this question, because this is really what I wanted to get more into measurement from the beginning and sort of just.
I think it might be absolutely. I mean, I think if we seriously want to get into like the foundations of quantum mechanics, it might be fruitful. I mean, for ourselves as well as for anybody listening, if we were to fully outline the foundations of quantum mechanics first. So that at least we have, so for instance, all these confusions that I was running into with respect to saying what the state of a particle is, but then that state of a particle is in a way perspective dependent, how I want to. And that's why it's very easy to get into these rabbit holes where,
Right.
Yeah, it's not very easy to delineate which one I want to take because I haven't seen the end. Yeah.
Right.
Which is
But that's
probably the purpose of this debate. Yeah.
right. I mean, I think that's part of the function. I mean, when we look at the debate texts that we have now, it's like they didn't just appear out of nothing, but the scholars who composed them actually
Right.
studied a lot and then debated a lot, and it's sort of gradually over many generations, sort of that kind of
Absolutely.
conceptual structure formed, and it was like, okay, now we can put this down on paper. Like, but it also, so I mean, it has this dual thing where it's like actual human beings went through their their debating and their reflection to come up with a sensible and cogent kind of theory and put it together. But at the same time, we can use it now as a basis to learn, right? So when we could still debate the things that are in it, even though it's sort of written up as if it's like the facts.
Yeah.
But for us now, like part of the making that kind of presentation, I think will take some debate, right?
Absolutely. Yeah, I agree.
Cool. So thanks very much.
This was very neat. Yeah.
That was very neat.
Yeah.
It's funny because I'm seeing how kind of solid the framework is, that it's hard to, I mean, yeah, okay, there are a few strikes in there, but not anything that really rattled the foundations of the theory, right? So
yeah, I mean, the tricky part is that and the trouble that I was facing particularly was in articulating a lot of my understanding into English. If that makes sense. Because oftentimes I think of superposition and wave functions and states in very mathematical terms that have very rigid mathematical definitions as to what a state is, what is a superposition, and what it means for something to be quantized. Then like quantization has a very definite meaning in that sense. So when I would translate into English, I would probably use very in a sense that's analogous to a lot of things people say, but it's just analogous, it's not exact. And that's why it's easy to fall into these logical loopholes where you as somebody who's done this a lot, you immediately see that where you could go and drag it into a loophole. So in that sense, I think it is a challenge, particularly with respect to quantum mechanics, at least when you're dealing with the foundations. And which is why, you're probably aware that there's so many debates over the interpretation of the subject itself, right? So I think, that's part of the reason. But I think the foundation itself, mathematically, I think it's very solid. It's the matter of interpretation in our usual human language.
Right, and I think it's funny because any, logical or philosophical debate about it is going to be using English term or any language, but going to be using words and not mathematics. So because we're trying to understand, well, what does it mean, right? And so meaning is not really like mathematics sort of abstracts the meaning out of what's going on. And so but it's still a valid question, like, okay, well, what is the electron? What is it doing? Does it change after you measure it or not?
Absolutely. Sounds good. Thank you, Losang. Yeah, I'll see you later.
See you.